Welcome back to Arxflix. Today, we're diving into a fascinating paper titled Spatial Tracker, Tracking Any 2D Pixels in 3D Space. This novel research explores the challenge of tracking dense and long-range pixel motion in videos by leveraging 3D motion estimation. Here's a glimpse of Spatial Tracker in action, showing how it lifts 2D pixels into 3D space for more accurate tracking. Now let's break down the key components of this paper. Traditional motion estimation methods, like optical flow, only handle motion between adjacent frames and struggle with long-range tracking. Feature tracking, on the other hand, tracks sparse pixels and can't fully capture the motion in a video. This is where Spatial Tracker steps in. Spatial Tracker estimates point trajectories in 3D space to overcome the limitations caused by the 3D 2D projection process. Using monocular depth estimators, this method lifts 2D pixels to 3D, employs a tripplane representation for each frame, and uses a transformer for iterative updates of 3D trajectories. The tripplane representation efficiently encodes the 3D content of each frame, making it easier to track motion in 3D space. This representation is compact and regular, allowing efficient feature extraction for any 3D point. Here's an overview of the Spatial Tracker pipeline, illustrating the process from tripplane encoding to trajectory prediction and ARAP constraint application. To estimate the 3D trajectories, Spatial Tracker uses a transformer for iterative updates. It predicts the 3D locations of query pixels across the video, leveraging feature correlation in 3D space for more accurate tracking. This equation showcases how the transformer input feature is composed during the iterative prediction steps. One key innovation in Spatial Tracker is the as rigid as possible ARAP constraint. By learning rigidity embeddings, the model can cluster pixels into different rigid parts, maintaining spatial consistency even during occlusions. This ARAP loss function encourages distances between points in rigid clusters to remain constant over time, enhancing tracking reliability. Spatial Tracker achieves state-of-the-art performance on various public tracking benchmarks including TapVid, BayDJ, and Point Odyssey. It excels in challenging scenarios such as fast motion and extended occlusion. Here's a qualitative comparison showing how Spatial Tracker outperforms previous methods like Co-Tracker in handling complex motions and self-occlusions. Spatial Tracker shows that incorporating a 3D representation is crucial for solving dense and long-range motion estimation challenges in videos. The use of tripplane representations and ARAP constraints significantly boosts performance. Future advancements in monocular depth estimation could further enhance the tracking capabilities of Spatial Tracker. That's all for today's deep dive. If you enjoyed this breakdown, don't forget to like, comment, and subscribe to Arxflix for more updates on cutting-edge AI research. See you next time. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.